Okay.
So how are the recorded lectures actually? Anybody ever looked at them? Of you? Yes? No? Maybe? No, it's mostly the people who are here don't look at the lectures. Yes? The sound sort of cuts out in some of them. Sometimes, yeah, there's sometimes also one of the cameras drops out and then I restart it too late. So some lectures you don't have the complete thing. But it's still possible to kind of roughly understand what's going on, which is the idea essentially, that kind of, it's not the same as being here, obviously, but it gives you a 90, maybe 80 to 90% experience. All right. You are 66 people. There are many people in one person. Fine, let's get going. Nonlinear control. And the good thing is, let's go recap for a tiny moment. What did we do in this course? We are now at the beginning of March. We started somewhere at the beginning of January. Besides some intro into linear algebra and differential calculus, we talked about linear control initially. Remember, linear control, PD control, PID control, block diagrams, a little bit stability theory, how to get a system going. And then we looked at some simpler systems where this applies, like the pendulum system. Cool. And then the big misery came that if you want to do nonlinear control, we have to go through a fair amount of basics in order to get there. And that basically went from coordinate transformation to direct kinematics to inverse kinematics to Euler and its Newton method until we finally get the nonlinear differential equations of motions, which we need for nonlinear. That's where we are now. So now basically after spending these extra weeks and all that, more kind of nicely developed scaffolding topics, we can actually do nonlinear control. And that's essentially what this lecture is going to be about. And you will see now suddenly how we can apply our knowledge of the system which we care about. And really for our purposes, I just want to re-emphasize, we will work with robots which stick to this standard equation of rigid body dynamics. Okay, this is a vector matrix equation summarizing all our knowledge about the dynamics of the robot. Importantly, this is again written as an inverse dynamics law at this moment because the torques or controls on the right side. If you want to write this as equations of motions, you have to basically solve it for Q double dot, which is not particularly complicated. If you wish to, Q double dot is obviously something like tau minus C minus G, and I leave out the little stuff which they depend on, times B minus 1. Okay? So that would be the differential equations of motions. They're not as pretty as our little pendulum equation and easy to understand, but this is what they are. You also see that in order to have the equations of motions, you have to be able to invert this inertia matrix, the rigid body inertia matrix, not to be confused with a 3x3 inertia matrix, which we normally have. It's called the rigid body inertia matrix because only inertial terms are in there. But it doesn't look like an inertia tensor or something like that. It's full of masses and inertial components. But it has to be invertible. Otherwise, it's not working, and you can prove it's positive definite and symmetric and whatsoever. Although, actually, if you really care about it, now it basically comes to, if you wanted to simulate a robot, which you will actually see when you get our simulator, we essentially have to do stuff like that in order to integrate the equations of motion. You know integrating equations of motion? Yes, no, maybe? Just a reminder, okay, x dot equals alpha x. If you want to integrate that, basically, if I wouldn't have to do that, but I can do it now, I have to basically compute at a certain time step delta t updates to my state x. So let's assume I start with x0 somewhere. So then what's the next step? Well, I can compute x dot equals alpha times x0. That gives me a time update. Let's call this a time step t equals 1. And then I basically do x dot t equals 1 times delta t plus x0 is going to be my x at time equals 1. sense? Simple, tiny little time steps going forward. I take the velocity, multiply it with a small time step that should be at an incremented position, add it to my current state, and get my next state. That's integration. Now, we can do the same here. It's just more complicated and way more work to compute. But what is interesting then, if you have a robot, a normal standard industrial robot, like clunky big thing, no worries. But it's interesting if you do this with a robot which has a big body like you guys and the tiny little lightweight fingers. The inertial entries for the lightweight fingers are going to be very small masses and very small inertia. So that actually the B matrix in a complicated robot which has big actuators and small actuators becomes algebraically fairly badly conditioned. So you can get condition numbers of 10, 20, 30, 40, 50,000. And then actually inverting these guys can become a little bit problematic. Just to remark actually that in general, simulating physical systems, when they become more interesting, is unfortunately not as trivial as the little Euler integration, which I just showed you. It becomes more tricky and you have to pay attention to lots of details. And it can go unstable and explode. And there's something you will see when you get our simulator. I promise you, you will make it explode occasionally. The good thing is it's just quits and you restart it. Okay, good. So that's our knowledge. Let's go through nonlinear control. And we're just going to we will go back to this knowledge very soon, but we start things in the simplest possible way and see how we can basically bootstrap things. There's basically two big topics we have to talk about. One is joint space control, and the other one is operational space control, which I'm not going to talk too much about. Despite it's actually a really interesting and maybe more interesting topic than joint space control, but it's a little bit more involved in its algebra. Okay, joint space control means I basically create directly my motor commands in joint space, which makes a lot of sense since that's where we usually live. Operational space control is, I think, in terms of my n effector, and then basically try to create motor commands in n effector space, which are kind of virtual motors since I don't have them, but try to kind of push them back into joint space so that where my real motors are. So we'll basically talk about both a little bit. Good. So let's see. That's what I just said. Cool. You can think about joint space control as solving two separate problems. The one is first you do a planning problem, usually in the external world. You do inverse kinematics to basically get your plan into the joint space world, and then you control things as if the plan had been generated in joint space. This is kind of a little bit of separating two problems, which is scientifically always nice, but has the problem potentially that, well, you basically make up a trajectory you want to follow in n effector space, put it into joint space, but if there are now some errors in the system, like maybe your kinematic is not as accurate as you put it into your equations of motion, and then your transformation matrices are not accurate, you potentially get actually low quality control at the end effector, despite you might be doing nice quality control on the joint level. Usually it's the best thing to control exactly in the space which you care about. This is essentially what operational space control is doing. It directly basically looks at what are my errors in task space and reflects them down into a motor command. In general, all these things have somehow explicitly or implicitly inverse kinematic stuff inside. And if you run your robot into singular posture, like remember this when we lose degrees of freedom essentially in our Jacobian, you get into trouble. Whether you see that directly or indirectly here, if you do inverse kinematics, you see it directly since you get a Jacobian, which basically becomes very badly conditioned when you try to invert it. In operational space control, you don't see it as directly, but the same problem happens. But let's do one at a time. Okay, joint space control. And there is basically two ways what you can do. And we're going essentially a little bit through what people have been doing in the past, because in the 80s and 90s, they didn't have enough computational power. So they had these tiny little crap processors and try to compute a few floating point operations, and that was a problem. So they try to simplify things, and still it's worthwhile thinking about that. So the idea is now these equations are complicated. So B is a big matrix, then C is a big matrix if you write it like this, and G is a vector of gravity stuff. Wouldn't it be nice if we could somehow make it something that this is not a big matrix equation, but rather that is like n for n degrees of freedom and independent equations which we can work with. This is kind of the idea of independent or decentralized joint space control. We try to basically find a first-order approximation to doing this without being that accurate. The good thing is you can do this very hacky. You can do this very fast. So what does it mean? Essentially, what I try to do is this here B is a big matrix multiplying times Q double dot. And then C is a big matrix, so this is B. This is C multiplying Q dot, and then comes our gravity vector. And I try to figure out, is it possible that I can just focus on the elements which are on the diagonal, okay, and ignore these other ones? And it's actually a useful thing to think about when this is valid. There's one possibility is you say, I simply don't want to care about those off-diagonal terms. And on the diagonal, what I should have essentially for every degree of freedom, and I should have chosen the main moment of inertia in the direction it is moving. So like if it's a prismatic joint, it would just be m times acceleration squared. And if it's a rotational joint, we go to our low pendulum example, since we've done this, it's theta double dot times, for instance, mass times length squared. Okay? So you can do this. You can simply say focus on this, ignore everything else. You make your life much easier. You do a rough estimate of these terms in here, and you're fine. And for those terms, well, maybe you just know that there's some viscous friction, and you just put in some viscous coefficient, like make it like B1 and B2, so just no viscosity. And gravity, well, you have to do your best bet, or you put in an integral controller which takes care of gravity to some extent. So this is like fudging your way through. And you can do that, and essentially you assume that these other terms are not important. And there's actually very interesting examples in the literature where people have been doing this to simplify their control systems. It's a very famous example, and this is actually called Rayburn hoppers. I'm not sure whether you've ever seen that. So Mark Rayburn was a professor at MIT, particularly in the 80s and 90s, and then he created Boston Dynamics. Many of you have seen Big Dog or the Atlas robots which come out of this company. But in the 80s, he had a very simple robot. It basically was just a disk with a leg. It was essentially a pogo stick robot. And it was just hopping around. And he basically didn't want to deal with these equations at all. And basically said, let me assume I can control this leg, which can swing back and forth independently, and the body is another component which I can control independently. And what he essentially does then in this case is that all these terms which are sitting here, there is just disturbances. And as long as I have a decent PD controller, the PD controller is supposed to reject disturbances or errors, and will hopefully take care of that, which is not a bad concept. He was very successful in the 80s, creating very simple controllers which work with us. There's actually other robots where these equations make sense. You played with the Now robot. And one thing which you noticed is most likely they feel there's a lot of friction in those robots because of the gear drives. And if you have a lot of friction, what really means that these terms here become very dominant. And what is interesting is not just basically if you look at the B and the C or maybe the G components, but also like is there one of these terms which outweigh the other ones entirely? So for the Now, for instance, these terms are much, much bigger, most likely, than these terms, and potentially even those terms. So you could easily argue that all the work of putting inverse dynamics in the Now robot may not be worth it, because it's so heavily dictated by friction that this is all what we care about. Could be. And it actually is true for some robots. So what is really interesting, actually, if you really want to analyze a robot, you try to basically figure out whether you can, when you run a robot, and use inverse dynamics. Okay, let's assume I want to create the following sine wave over time. So just for 1 degree of freedom. Q, oh, sorry, this is Q, this is time. Okay? We agree that this is position. That's what we want to track. So let's call it Q desired, to be really precise. And then we also agree that we have velocity components. And we get also acceleration components. Cool. Very simple. They're sine waves. Now what is interesting is now if you create with our inverse dynamics this tau, or let's call it u, our feed-forward command, and then you plot u versus time, or u feed-forward, which you computed. Okay? And it will have some wave too. Interesting question is, how does this wave look like? And it can look complicated, and it's very hard to figure it out, particularly in a multi-degree of freedom robot. But sometimes you will notice, for instance, that it is kind of the same kind of a sine wave as velocity. So now this would correlate with the orange one. If that is the case, you actually know that seemingly some of the friction terms become dominant. If it correlates with acceleration, you know actually that some of the acceleration terms are dominant, and the inertial terms are dominant. So you can actually figure out from these plots a little bit who's the most in charge creating the feed-forward command, which is really helpful. Now you would have to do this at different velocities. Obviously, if you do this very, very slowly, the only component which is interesting is gravity compensation. If you do it fast enough, when you have significant velocities, you should see that. If you have significant accelerations, you should see that. So, but that is how you start now analyzing a robot based on our model knowledge and try to figure out what's happening. Okay, so, fine. Essentially what we, let me, do I have a picture? Yes. When we do independent joint space control, we basically just create a PID controller or something like that for every joint independently. So we create a proportional gain, an integral gain potentially. We create a error, what is that? du dt. Proportional derivative, du dt, error velocity. Okay. Okay, that should be proportional integral. That should be velocity. Oh, this is the math. Sorry, that's a simulating block. That's why there's a u. It should be dp dt or dq dt if you want to do this properly. So this is velocity, and you can even take acceleration. So people are not just doing PID control. That's what you know. They also added an acceleration term, which is kind of a cheap way of doing inertial compensation for every degree of freedom, independently, assuming it behaves like a simple pendulum or like a simple translatory mass. Okay? This is what you can do. This is fudge. The nice thing is you can do it fast. You can hand-tune these gains and see how much of a decent controller you get out of that. This is a little tricky with the accelerations, and if you differentiate things twice, a noisy position signal becomes really noisy. So you would have to filter this and smoothen that out. We'll talk about filtering, but it will be some work to get this going. But then you add it up, and this is done for every joint independently. You give it to your robot, and essentially what you're doing is you pretend it is a linear system, since you can treat every degree of freedom independently with constant PID and maybe acceleration gains. And then the nonlinearity is basically treated as if it were a disturbance, which is added there. And you hope that your error correcting, your negative feedback controller will take care of that. This is hacky. But you know, if you're sitting there, you got a new robot, and you just want to get going and want to get a first feel for the robot before you go through the math and doing inverse dynamics properly and all these things, this may not be a bad first shot to just see how well this robot would perform. And how you try to check this out, and in the end, you get in with something like a desired sine wave for every degree of freedom, and you see how accurately you're actually tracking the desired with your actual controller. You will actually see that visualizing what you're doing in terms of the desired trajectories and the actual trajectories, the feed-forward commands, the feedback commands you're sending out, it's very critical. So this is what we do as daily debugging tools to actually understand what a robot is doing. And it takes some time to get used to that. We have some special MATLAB tools to visualize trajectories and superimpose them and make things nice. I'll show you that a little bit later. Not today. Okay, good. So super simple, but still good to know you can do that. Just to get started, quick. One day, you got the robot today, you want to see a little bit tonight, that's what you do. The other stuff, you will spend some days or weeks. Okay. Now, if this is all not appropriate, then we have to go to proper dependent or centralized joint space control. People call this decentralized and centralized, but decentralized means you could actually put a processor at every degree of freedom and implement it there independently without knowing about the other ones, which is, from a modern world of multiprocessing and distributed processing, very appealing. For all the other stuff, like if you want to compute those equations, you have to get a central processing unit that gets all the knowledge about all degrees of freedom, and then it can compute these equations, and you need a little bit more power in the system. Okay, makes sense? Good. Now, we go one step forward and do some semi-independent joint space control. Okay, no, well, I'm not sure what is this about. Fine. We basically will start to add a feed-forward controller in this outer loop and have our negative feedback controller as here. So this could be the PID controller. And now we create really feed-forward controls not based on negative feedback. So let me go back here. So this here was all done with negative feedback. So everything was compared against the desired. Now we actually take something from the desired directly, run it through a feed-forward controller, and try to create an appropriate feed-forward motor command. And what we're going to end up with in the end is that we get a complete motor command, which will be composed out of a feedback term plus a feed-forward term. And that is essentially what this sum here would be realizing. So the negative feedback controller can be whatever we've been using before. Now we can basically put additional terms in here. And the additional terms may be, for instance, what I mentioned before. We can put in here an acceleration-based controller. We say basically here, U of f is simply Q double dot times some A, K, Ka. So that would be a very trivial way of creating a feed-forward controller, just trying to compensate for some inertial terms. Okay? And that's essentially what we just did before, but now we do it based on desired. But we want to do it a little bit better. So let's go to the first slightly more complex controller. And this is called computed torque feed-forward control in the literature. It looks more complicated than it is, trust me. Not that much behind it. The whole idea is that my favorite equation up there, let's simply take from our desires the knowledge and put all the desires in here. And then call this here UF. Okay? You have a desired motion which needs to be composed out of position, velocity, and acceleration. If you don't have acceleration, well, then you're missing an important part for fastly accelerating movements. You could still do it without, but it will be worse. So this is the proper way of doing it. You put all the desired, and now you get a feed-forward command through time, which you just add into the system. And this is literally what is called computed torque control. And now here's just basically development. What is this thing actually doing? Is it actually a good controller or not? What it's assuming? So this is our standard rigid body dynamic, so nothing profound. And now I'm plugging in the control law, which I just wrote here. So I basically, instead of the tau, I just plug in everything based on desires, okay? And a PD controller as well. This is a PD, P term, E term. So not too profoundly new for you. And then comes now a step which is typical when people try to analyze what a controller is doing. You define an error. And the error here is Q desired minus Q. Then there's an error dot, which would be Q dot desired minus Q dot. You can even get an error double dot by taking one more differentiation. And you start basically sorting the terms and try to rewrite these equations based on errors, which basically looks like this. Again, I think I don't have to do this. It's just sorting terms which have Q dot and whatsoever. But there's one important, basically, assumption behind this. Essentially, you're assuming that when you compute B of Q desired and B of Q, so B of Q desired and we have B of Q, you assume they are roughly the same. That means Q desired is not too far away from QD. Only under these circumstances, I can basically write an error term. Remember, this here is multiplied with Q double dot desired. This is multiplied with Q double dot. And then I'm writing suddenly B of Q times E double dot. Well, that only works if B of Q and B of Q desired and B of Q are actually the same. Otherwise, I would not be able to do this manipulation. So the idea here is that if you're basically starting your control close enough to the desired, which is not very hard to do, you make your desired always the same as your initial state. Then you can finally write the robot error dynamics as shown here. Now, is that beautiful? No, maybe, what's about? What is important about this equation is something very simple. There's E double dot here, there's E dot here, and there's E. They are multiplied by some matrices. And in general, this is called a second order error dynamics. Second order, linear error dynamics. And for things like this, you can actually prove that they will converge to zero error if all those quantities are estimated correctly. So we always like these ideas. We like to get, in robotics for proofs, we like to get some error dynamics which looks like this and show that this is zero, and then we can show that this converges, the error will converge to zero to fulfill these equations. Okay. Good. So this is the first more complicated control law. Important feed-forward commands are based only on desires. And higher derivatives are usually easy to compute. That's nice. So this guy here, for instance, it's based on my plan, my Q double dot desired. If you create a noisy Q double dot desired, you're an idiot, okay? That would be really stupid. If you make up signals, make them up without noise if you can. Otherwise, you're just killing yourself. So again, always go to my little sine wave example. I plan Q desired as a sine wave, then I get Q dot as a derivative. It's smooth and beautiful, and Q double dot, I could take derivatives for the end of my life and get smooth signals. So I will never create nasty signals. So this is nice. So if you're deviating too much from the desired directory, then our feed-forward commands are not very good, and we have to rely a lot on the feedback controller. And what is nice, if you have a cheap processor, you can create a plan and can compute the entire feed-forward commands offline and store them. So you don't have to do this online, so if you have no processing power. Good. Now, this is nice, but it has some pitfalls. And now we want to go to proper inverse dynamics control. So this is inverse dynamics control, but the real nice way is more complicated. And here is an example where the little compute torque controller will not work so well. And all of you are actually living examples of that. So here's a pendulum. As you notice, I love pendulums. Now the pendulum is basically upside down or an inverted pendulum. And I would like to have it at this position. Okay? I have a very simple task. Let's call this here the angle Q. And I say my Q desired equals 0, my Q dot desired equals 0, 2. Okay, cute. More of that. Q double dot desired is also 0. I want the darn thing to be upside, basically staying up straight. And I use a feed forward from this computed torque control. Let's call it computed torque plus U feedback, which is our standard PD controller. Okay. Now, is that going to work? It's a really cool inverse dynamics controller. And the answer is no. It's very easy to see. Okay, let's compute the feed forward command for those desires. So how much torque do I need down here, motor command, to keep the pendulum upright? What do you think? 0. It's just standing upright. There's absolutely no torque needed at all. So in this little example, we would always compute 0 for that. Then we just have the feedback controller left, which is now, I just chose it to be a PD or not a PID controller. It means you will never reach up there, since you will always fall over against gravity a little bit, so gravity goes down, and then you will hang against the PD controller, since the PD controller can only create a command if there's an error. Without error, no command. So this controller doesn't work. All you human guys are walking upright. You do the same thing. It would be really annoying if you would always fall over. So there's something which needs to do more profound control. And that's essentially what we're going to do now. So we're now going into what is called proper inverse dynamics control. And I want to show you once how this is done. In the simplest possible example, and this is actually this kind of gravity compensation example, very similar to what I've just showed you. Time-wise, we're doing okay. Okay, so how do you develop nonlinear controllers in general? It's a little bit of an art, voodoo, inspiration, and some generic recipes. One favorite recipe that people like to use is what is called feedback linearization. And the idea is that I have a control system which is by itself officially a nonlinear control system. It shouldn't be linear right now. But what I'm going to do is I create a feedback loop with some computing box here which feeds back into it, such that if I would draw this boundary about the system like this, it would behave like a linear control system. Essentially what I try to do is I try to cancel all nonlinearities. Not very hard, you know, we have our knowledge. If you already noticed, that's what I try to show you in the compute torque control law. If I can compute B of Q desired times Q double dot, and basically say, okay, my system is current, that's my motor command. My system has those dynamics here. If I can create, if Q desired and Q are close enough, then these two terms will cancel in my equations. So I can actually reduce the equations of motions to become very simple. And we'll just do this now in a slightly more profound way. And for that, let me just switch to the book one time, since he develops this really nicely. Exactly how you should be doing that. Whoops, here we go. And this is, in a nutshell, how people try, or many people try to develop more complicated controllers. Okay, for me, the challenge of the day is to basically recreate this on the whiteboard without making too many mistakes. Cool. So we want to do a PD control law with gravity compensation. So very important. That means we have a desired. So let's write this down. Goal. PD plus gravity. Which is one of the most useful controllers you need for almost anything, since if you have a system under gravity, the first thing is you want to make go somewhere and hopefully hang out against gravity. The one that is sagged down all the time, which would happen in a human-like What this means practically here is that we have a Q desired, capital D, little d, sorry, little d, which is given. But we assume Q dot desired equals 0, and Q double dot desired equals 0. That means I just want to support a particular posture, but then I want to stand still there, and I want to be there as accurately as possible. Which is literally the little pendulum example which I gave you. Now we just do it for the full-blown rigid body dynamic system. Cool. Now we need to define the same variables as he does. We need to define what, and I don't know why he likes squiggles, but that's what the control people often like. Instead of error, they write Q squiggle equals Q desired minus Q. Okay, that is essentially an error term. We got that. Now we do something really cool. We define a Lyapunov function. Who knows about Lyapunov functions? Yes, a little bit. Excellent. Good choice. Another person. So you can explain it to them after. Now, fine. What's a Lyapunov function? A Lyapunov function is something. People call it a potential function, essentially. The idea is you make up a function which looks like a ball. Boop. So this is a ball. Think of it. 2D. You make it 3D, 4D, 5D, whatever you wish. Okay. And let's assume we have a robot which might be defined by some states. Which this here might be Q1, this here might be Q2, just some states. And I want to be at a particular point here, okay? This is in the Q1, Q2 thing. This here is my potential function. And what I do, I create this function. And just for simplicity, think of it as a parabolic bowl, which is most of the time the right way of thinking about it. I want to put it right on top such that its lowest point, the minimum of that potential function, sits where I want to be. That's my desired. Q1 desired, Q2 desired. Okay. My bowl has to be defined as a function of state. Okay, so that's the space I've created. Now, let's assume you start somewhere in your Q1, Q2 space. That means actually if you're somewhere here, it would be a point up on the potential function here. If you now can show that with a particular control law, PID control, feed-forward control, is exactly what we're going to develop, we can show that dV dt is less than 0. That means for every time step I take under my control law, V becomes smaller. Now that's very cool. If V becomes smaller, I can only go down the bowl. Guess how far I can go down the bowl? Only until I'm down there. That's the end of the bowl. This is all I define this. Okay, it's my world to make it up. That means if I can show that this holds, I will always reach the bottom of the bowl, and I will basically reach my goal highly accurately. That's one of the main principles how people think about how to develop controllers and also how to prove that a controller does something correctly. And I just showed you for this super simple example. It becomes way more complicated than nonlinear complicated example, but the good thing is we don't want to go into that. Cool. So the Lyapunov function, now you have to make it up. And the negative message of the day is that making up Lyapunov functions is, for a complicated system, a piece of art. And here's the beauty of life. Just because you cannot find a Lyapunov function to show or to derive a controller or to prove a controller, doesn't mean it doesn't exist. Just means that you couldn't find it. Kind of embarrassing. So not finding it is not a proof of non-existence, it's just a proof of ignorance. Finding it, however, is cool. And there's many people who find important Lyapunov functions for certain control systems, and they got very famous for that. because they could certainly say, hey, that airplane stays in the air. Patent, give me money. Cool. And then you become rich and famous and live forever after until you die, but with a lot of money. That's good. Cool. Now, let's create our Lyapunov function. Well, it's not so hard for our particular world to figure out what is a good Lyapunov function. What do we want to achieve? We want to drive that error to 0, and we want its velocity to go to 0. So our state space is essentially spent by q and q dot. That's our normal state on the robot. That means it would be nice if I create a Lyapunov function which first has a component which depends on the error. And that's what the first term here is going to be, or the second term. Fine, second term. And we do this 1/2 q squiggle is our error, transpose times q squiggle. So this term is nothing but the inner product of the error, how far I'm away. If I get this to 0, I'm at the bottom. It's a quadratic bowl. If I'm not at 0, it goes up. Make sense? Super simple. I left some stuff out. I know. I will get back to that. And let's put another term in there, and this concerning velocity, since I want to be at 0 velocity. So q dot transpose times q. Cool. I made up a really nice bowl. Okay? That means 0 velocity is my goal. It's literally a parabolic bowl in a high-dimensional space. I don't know how many degrees of freedom my robot has. And I'm at velocity 0, and position error is going to be 0. So that is exactly what I want. But not so hard. So for simple systems, we can do little bowls like that. Now, the right thing to do now is to do the entire analysis. And what we have to do is essentially figure out dv dt. And this is how things work. You start with something simple like this. You do your analysis, push it through. You figure out something didn't work. You go back to the design, change your Lyapunov function, do it again, and you iterate until you get what you want. Now, I don't have that much time, so I basically put in something which is going to be helpful. And I basically kind of put in B of Q and KP here. So he basically puts in the rigid body inertia matrix, and he puts in a proportional gain matrix. Okay, so B of Q is depending. It's not a constant. It depends on Q. Maybe I should make that explicit. That makes the story a little bit more complicated. But KP is a fixed matrix which does not change over time. All right. The rest is now just an exercise of differentiation and a little bit of extra knowledge. Okay, this is almost fun, maybe. Good, dv dt, or simply called v dot. How to do that? The fact is 1/2 I just put in there because I know I do differentiation, and I differentiate something which is quadratic. I get a factor 2 in my 1/2 slowly. So I have to now differentiate this here, and this has to basically be done with the chain rule. So I get q double dot t times b times q. Actually, this still has a 1/2. Then I get another term, which is 1/2 q dot b dot times q. No dot. No dots everywhere. Sorry. Plus 1/2 q dot b dot q double dot. Okay, so and I should put inner products in there when I need them, so they're useful. Even though this is an inner product, we know these are scalars. Okay, they're non-vectors. That means this term here and this term here are the same, because I just can transpose them and scale of a transpose of a scalar as a scalar. That's why I can essentially eliminate the 1/2 and get rid of one of those terms at least. And then I have this guy here. See that I managed to do this. We have 1/2 q squiggle dot kp q squiggle plus 1/2 q squiggle kp dot. Okay. Same story. It's an inner product. Creates a scalar. So I don't have to keep both terms around. I just need one of them. See how much I accomplished. Did I do something reasonable? I have the Q double dot guy. Okay, he has the Q double dot on the other side, which you can just transpose it because it's a scalar. What else? 1/2 Q dot transpose B dot Q dot. And here he has minus Q dot transpose. How did he do that? Bloody hell. Okay, fine. Very simple. What happens if we do Q squiggle dot? And please notice that Q desire is a constant. It becomes minus Q dot. All right? That means I can replace Q squiggle dot with Q dot and putting a negative sign here. Okay. That's a nice thing if you do it on the whiteboard. We can do step by step, and hopefully you can see how this came into being. Okay, and we are kind of happy. So fine, we put the double dot here, which is most likely more reasonable for developing equations. And the next thing we got to do is essentially we got to plug in our knowledge of Q double dot. Q double dot comes from the equations of motion, so it's always the same game. And we actually know that B Q double dot has to be, what is the use for motor command? U minus, and he uses now little g. Fine, I can use little g as well. And, no, sorry. That's not what he will use that later. Yeah, he does use it. Sorry. And he uses minus c. Okay, makes sense? I just rearranged the rigid body dynamics equation that B Q double dot is on one side, U minus G minus C is on the other side. Okay, fair enough? With me? And then I replace this term in here. That's all. So I basically plug in my entire knowledge of the dynamics. As an aside, he uses actually some equations of motions which have an additional damping term. So he has a, in this case, minus FQ dot in here, and I just skipped that term, forgive me. It's just basically assuming the robot has a viscous damping term. Not really critically important. So this is this term, and I just leave that out. Cool. And we now have to start sorting terms again. So everything here which depends, if I plug this in, how much time do I have? So this big term gets plugged in, so I get V dot equals, I just do it a little bit, I'm not sure that I go through the entire misery, times U minus G minus C. This is this part. Plus 1/2 Q dot transpose B dot Q dot minus Q dot KP Q squiggle. Now we multiply things out. What we want to do is essentially we want to have all the terms which multiply Q dot, for instance. We want to sort them together. And other terms which multiply Q squiggle, we sort them somewhere else. So that's what he does here. He basically tries to figure out, so who is multiplying Q dot? And he basically figures out, so Q dot is multiplied by B. Where does the B come from? Oh, B, no, I just replaced, oh, the B dot, sorry. B dot here. Q dot multiplies B dot. He gets this term. And then he gets suddenly two C's here. We have only one C. But he combines these terms and pulls 1/2 out. So if you put the 1/2 back in, there would be just one C. And he writes it like this. And he writes the other terms just as before. And now comes a small piece of knowledge which you would not have at this moment. He does that obviously for some reason. And the important, so let me see what I can bring up here. We have it on the slides. There's one important piece of knowledge, which is V dot of Q minus 2C of Q dot times Q dot. And someone in the 80s figured out that this has to be always 0. Cool. Okay, that takes you a while to show that. It's shown in the book somewhere, how it's derived. So that's something, okay, this is relatively young knowledge. I think it took them when they figured this out in the 80s or the early 90s. It's not that old that people figured it out. This is now some people doing rigid body dynamics theory, looking at this and something out, oh, this must be 0. And because this must be 0, well, we are very happy. It's the null matrix, as he calls it, and we can basically eliminate this term. Now that makes this entire misery here much easier, and that I can write down again. Oof. We now get V dot equals. First term goes away. I ignore the friction term here, and I'm left with Q dot transpose times U minus G of Q in his notation minus KP times Q squiggle. Okay, now let's write it out. This is going to be Q dot transpose times U, just I multiply all the terms out, minus Q dot transpose G of Q minus Q dot transpose GP Q squiggle, is that correct? Q squiggle. What I would like to show now, let me see, everything. Yes. What I would like to show now is that this term is always less than 0. Okay? The way I would be doing this normally, I would start now to analyze. Is this term strictly less than 0? Well, Q dot transpose times the motor command. I don't know. Q dot times the gravity term. I don't know. How about this term here? I don't know either. So, complicated. Often you find some terms which are strictly 0. Sometimes you find terms which are strictly 0, and you can show that all the other terms which are not strictly 0 are definitely overwhelmed by the term you care about. In this case, we can do things a little bit nicer. So again, we want this here to be this 0. And given that this is more complicated, we still have one little parameter we can wiggle with. We have U. We can define U as our control law. We haven't said at all what it is. So how about we say U is simply G of Q plus KP times Q squiggle. So that means gravity compensation as feed-forward command and a simple P controller as feedback command with the arrow. Well, we can plug this in. If I plug this U in there, then I get this here to be equal to 0. It's not less than 0, it's equal to 0. The reason why it does that is because I only put a P controller in there, not a D controller. If I had put also in my entire scenario, in my Lyapunov function to start out with, a term which basically says Q dot transpose KD times Q dot transpose, and it times Q dot, then I would get an additional term which is going to be negative, and that would switch it to negative. He basically accomplishes that by having this automatic damping term in here, this F, that is equivalent to a viscous damping term in the robot dynamics is equivalent to having a D gain. in your PD controllers. Okay, so in the end, all I have to do is essentially I have to augment this and add a KD times Q squiggle dot in there, and then I have a control law. If I plug this in, it will be strictly pushing me into the negative. And I can basically say this is going to be a stable control. Okay, so a little complicated, but actually a useful exercise how to do that. Okay, he has it here, and I should put it in negative, sorry, bad, minus Q squiggle dot, and you know that, well, that's actually correct. I put plus KD times Q squiggle dot, and now Q squiggle dot can be replaced with Q dot, as we showed here, with a negative sign. And then you can see if you multiply this with Q, you plug this control law in there, this term cancels, this term cancels, this one stays alive, and you get additionally a term Q dot transpose KD Q dot. That is strictly negative. And that basically proves that we are going to be always less than 0, and that means we go down to the bowl. So the old story actually, just re-emphasizing, you need to lose energy in your robots. Otherwise, you can never prove stability. Someone has to dissipate energy. Cool. And this is the control law. This is the picture which goes with this control law if you want it nicely. So basically, you take the normal control law. Here is your P controller. Here is your D controller. The D controller wraps around as a negative term. This guy. The G gravity term, very important, it's now computed not based on the desired, it's computed based on the current state, feeding back into here, and then you just have the P controller coming in, multiplying the error. Make sense? And that is called feedback linearization. Basically, with the help of this term, we are linearizing this manipulator to behave essentially in the scope of which we care about, like a linear system. And we then can control it with a K and P controller, with a P and a D controller without any problems. So this thing now would guarantee, if you don't have modeling errors, very important, if you don't have modeling errors, it is guaranteed to get us to our desired. Very different. So you can now look at it. So how does it compare to the example I gave you before? Let me just touch of space here. I gave you this little inverted pendulum example, which I would like to get to this position. So this here's my Q. I wanted to get it to Q desired equals 0. Would that work? Oh yeah, absolutely. See what it does now is the controller computes at my current position gravity compensation. Okay? It computed at Q, not at Q desired. It means I'm also, from that point of view, I cannot fall over anymore if my gravity model is correct. And then, because gravity is already taken care of, my PD controller can push me forwards to the goal, since it's not fighting gravity anymore. Then I get closer here. I'm just going to be in this position. I recompute gravity, has changed, becomes a little bit less. And my PD controller can push me further here. So suddenly that works quite nicely. So the pitfall of the compute torque controller is gone. Neat. Good. That's what I wanted to get here. Let me quickly check what else I want to get here. So we are now feedback linearization. We've done that. And we now do this just for the case where our desired position is 0. Desired velocity is 0. But we can now pull this through with a time-varying desired velocity as well. And that becomes an inverse dynamics tracking controller. You can look in the book how it looks like. It's the same principle. It's just more complicated to derive. It would take longer. And you wouldn't learn so much novel things. It's more complex. But in the end, we do the same thing. We do rigid body dynamics, and we create a control law, which has now an acceleration term. It now is going to, because we're moving all the time, it's going to feed back the Coriolis forces, the gravity forces, all of these things are just put in to cancel those components. And we have a special acceleration term in here for the reference. And that's usually my desired acceleration plus some additional correction terms to make sure you reach the goal. And this is then becoming a proper inverse dynamics control. Small problems is that you may need higher derivatives sometimes, and they can become noisy. You definitely need velocity in here. Velocity is usually the numerical derivative of a position sensor. That's already noisy. You can also see, let me just go back one more time. If you would have delays in these feedback pathways, you would feedback stuff which is not true anymore. So if your gravity term, if you're moving your pendulum up, and your gravity term comes in with a second delay, well, by this time my gravity has already changed, so what I'm feeding back is not good. So you need fast control loops for that. Okay, so let me just mention for the end of the lecture, we talked about joint space control so far. Everything was done in joint space. And now comes the entire story in operational space. And the idea is really now, instead of having my PD controllers or whatsoever in joint space, I think about them in task space and then push everything back. And I'm just going to mention that quickly to you. Let me see whether I find in the book the pages I care about. It should be somewhere down the road. So he basically shows the development of the inverse dynamics controller the same way. More work, unfortunately. And then come robust control. Control is a pretty long picture. But here's essentially now the first version of a task space control or operational space control. Both of them are used the same way. Same words, no, different words for the same thing. And what's happening here is actually quite simple. So for instance, you create a desired X in task space. Okay? And you create also desired X dot desired in task space. And now you can convert that. You can, well, let's create a very simple controller which says my desired in X dot reference is going to be X dot desired times plus X desired minus my current X times some gain KX. What the hell is that? So I have a robot. Let's go back to my little robot picture, make it a two-joint arm to be super simple. These are joints, Q1, Q2. This point here is called X, okay, in a 2D or 3D space. So there. Okay, and I want to be somewhere here. And then it's going to be X desired. So I create a very simple law which says my reference velocity up there is basically dominated by my desired reference, my desired velocity. But I put in a correction term which is based on whether I'm really tracking my desired properly or not. Is there an error? Now I have this X reference. This X reference I can run through some pseudo inverse, which we know how to compute to get a Q dot reference. Okay? That's what our inverse dynamics computations were trying to do. And then you have the Q dot reference. From this, you can numerically integrate it to get Q reference. And if you want, you can also differentiate it to get Q double dot reference. And then basically run this here through your inverse dynamics controller and track it. And that would actually work. Has some problems, but it would work. This is essentially the basic idea of what is called Jacobian inverse control. You do basically a simple planning in external, in operational space or task space, and then we push this back through with a simple controller into joint space and do then joint space control potentially with an inverse dynamics controller. So this is one way of doing it. And this here just shows you the feedback here has to go through the forward kinematics or direct kinematics so that I can compare X desired with X. There's also, if you have an external camera and you can observe your fingertip, for instance, in your target, you can actually get the signal, for instance, directly from a sensor. Okay, so this is one way. And the other way is shown here. Let's blow this a little bit up. This is called Jacobian transpose control. What's different about that? The idea now is let's create, again, I need actually my little picture. I should get rid of it. Here's X. And there's some X desired again. Let's create a full-blown PD controller in joint space, in external space. So we now create, let's say, a PD controller in the X space, which is going to be something like kx times x desired minus x plus kx dot times x dot desired minus x. And this is my, I interpret this as a force in the X space. So that's kind of a force I would like to apply to my end effector such that it goes closer to X desired. Okay? The question is, how do I get a force back into joint space? It turns out to be amazingly simple. Jacobian transpose times Fx equals torque. Now, does that make sense? Well, you can think about it for a tiny second. You can actually derive it. Just give you a slightly more complicated robot. And now we do an experiment. Let's assume in this robot we apply a force F here at the tip. How much does every joint have to work so that you're not moving it off? Okay. Well, that you can figure out is because you force times moment arm relative to every joint, cross product, is the torque, which is going to act there. And so basically I can do this for this joint. This is my moment arm in this case. I can do it for this joint. That would be my moment arm for this joint. This here would be my moment arm for this joint. And if you now go back to when we talked about the geometric Jacobian, that's exactly how the geometric Jacobian is built. Basically looks at every point, it looks at the tip of the end effector and looks at basically how much can every joint contribute to moving it, which turns out to be equivalent to what is when you have a particular force, how much it can actually push against that degree of freedom. And that essentially is what's behind this here, that you can show that a force at the end effector can be trivially pushed back into joint space just by knowing the Jacobian transpose, not even inverted, just the transpose. That's essentially what this thing is doing here. So you have the desired, you get your direct kinematics feedback, you get a delta x is an error. If you multiply it with a gain matrix, so this is these two terms here, then you run it through the Jacobian transpose, and you send it to your manipulator, and you can control. And there's a whole bunch of control schemes which are based on this. Whenever it comes to what is called force control, you start using Jacobian transpose, and actually controllers, because you don't do matrix inversions, controllers become often simpler. Not necessarily easier to understand, but simpler. Okay, so this is what I wanted to get across today. Nonlinear control. We started from simple decentralized controller, centralized controller, only using desired, and finally with what is called feedback linearization, using feedback from the state to make our nonlinear robot behave like a linear robot, and then we can do proper inverse dynamics control. Knowing that, then we can add this additional component. We just did this fast, operational space control. We can easily use our knowledge and create controllers which are based on information at the end effector, not just in joint space. And there are simple ways how to push end effector information back to create torques in joint space. So here are the most basic, I think, nonlinear controllers which you get confronted with the moment you do nonlinear control. There's one important component. We do depend on the quality of the models. So if your B and C and gravity terms are very crummy, or you have unknown dynamics in your robot, like from hydraulics, cables, cable stretch, all kinds of stuff, then these model-based control laws start degrading. That's a pain. Particularly when it comes to now humanoid robots are pretty popular and many people control them. There's a lot of stuff attached to them. Cables, wires, stuff, all this creates dynamics. And the models we have of them from just pure looking at the computer-aided design stuff are just maybe 70 to 80% approximations of the real model. So there's ways how to estimate models. We'll talk about this at some point a little bit. But getting good models for model-based control is critical. All right? That's it for today. Thank you.